very elementary, basically, some thoughts on how one should understand WKB analysis, not for a single differential equation, but for D-models. So the case of single differential equation is very classical and nevertheless very interesting. And the case of systems is more difficult. So I will start by giving some reminder on WKB for D-models. So suppose we have a smooth algebraic variety over the field of complex numbers. So then, so basically, what happens if you have a single D model, dx model? Let me put one D model M. It has characteristic variety inside a cotangent bundle, which is conic. Conic and coisotropic. And conic because only the highest symbol of the operator is invariant. Now, if you pass from a single model to a family, then one can do more, one parameter family. That's called n tau or something like this of D models. It allows to refine this characteristic variety to a non-homogeneous one. Refines to a non-conic one. So basically, just symbolically, we may have a characteristic variety of some multiplicity 2, like the zero section, and it will be refined into something which will cover 2, 2, 1. So and this can be said in the most naive way, and it can be said in a more sophisticated way using deformation quantization. So let me first say that in the most naive way. So when I have a family of D models, say T tau lies in the complex plane. So we have the tensor product, simply the product of the ring of differential operators and the polynomial ring. And we use models over this ring or equations with coefficients in this ring. So models. Equations. Well, for instance, so basically we say have a differential operator depending on a parameter. For example, in one dimension, we can write something like dx squared minus t tau squared w of x, v of x times psi equals 0. In this case, tau is 1 over the Planck constant. But it doesn't have to be tied exactly like this. We can write like this, something different. Dx squared minus v of x, and we can say plus tau squared times identity. That equals 1. But this means that tau squared is the energy. But we think of tau as being large. So tau. It simply means that we count in we introduce a filtration in which it has an order 1. We can say that order of tau and also order of derivatives is 1. And order of coordinates is 0. So in this sense, they have a different concept of highest symbol. Like in this case, this and on those two summands will be the highest. And in this case, those two summands will be the highest. But it will be invariant. So highest symbol in this sense is still invariant. So and then if you have a model over this, then we can take it support of the associated gradient. So now, because we have one variable, it would lie in T star x cross C with variable tau. And it will be conic here. But we can put tau equals 1 and get a non-conic in T star x. So let's call it, characteristic variety with respect to tau of M. So it's sometimes called the spectral, can be called the spectral variety, or maybe called the tropical characteristic variety. I don't know a good name for this. Probably this. So for instance, in those examples above, it would be, we will have either p square equals v of x for that one, or we'll have p square equals minus 1 for that one. And that's so this would be a hyperelliptic curve. This would be a union of two lines. And it refines p square equals 0, which would be an ordinary characteristic variety. So now this, of course, is a very naive point of view, and this is embedded in more than one sense into the deformation quantization viewpoint. So on the cotangent bundle, as Pierre Schapira was explaining, so there is a sheaf W, we'll call it W T star x. So the sheaf of formal H differential operators, to a sheaf of C of tau inverse algebras on the cotangent bundle. And the naive ring of polynomials is embedded here. And so we can say that the tropical characteristic variety is simply support of M, or rather pi upper star, the pullback of M, tensor down. This is one point of view. And there is also, by looking at this, it maybe not the only point of view on this. Another would be, let's call it tropical viewpoint. It's almost the same, but it allows for a little twist. So it means that we start with variety x, and now let's multiply it. So let's say H is 1 over tau, and simply multiply our variety, build the field of Laurent series in H. So then this is a variety over a non-Archimedean field. So, over. So what we are studying in this way can be formulated by saying that we consider differential operators of this variety over this field. But now, once we look at it like this, we consider variety of H, variety over non-Archimedean field. So that's a constant variety. But we can consider non-constant variety, which varies. So can more general variable, so to say, families x over, which do not come from a single variety, and can even degenerate. So it can be, we make a picture something like this. So it can degenerate. So it will be a picture for a model. So model over the ring of Taylor series in H. And suppose the model has divisor, so the special fiber may be singular with normal crossing, with normal. So then there's another interesting concept, and we can still will have some kind of characteristic variety of M would live in something like T star x0 of log D. So again, will be non-conic. So it's interesting to look at this from different points of view. So it's a kind of it's a beginning of tropical geometry, but for differential operators. Now, the classical WKB method looks for solutions in some particular shape. Would be something like this: e to the tau phi of x, the oscillating term times the perturbative series, sum I equals 0 to infinity, ri of x, tau minus I. So this is a part of a space or a sheaf, let's say e to the tau phi, or x tau inverse, which is a module over d of t. So it's d of tau module. So we simply we can say that we look for home from our module to this. And then the classical formula is this, so that on phi we have the Hamilton-Jacobi equation, or characteristic equation, which means that the graph of d phi must contain in this tropical characteristic variety of M. And on the individual coefficients, the so-called transport equations. So this equation is nonlinear. On RE would be so-called transport equations, which are linear and recursive. So each one has on the right-hand side the result of the previous one. Now, from the deformation quantization point of view, this expression is simply an irreducible or simple module over this sheaf W. So this is simply whose support is on the Lagrangian variety. This is a Lagrangian. So now when the module M is holonomic, the family is holonomic, then the characteristic variety is itself Lagrangian. But not homogeneous. So we think of it as being a ramified cover. So it's we can think of a graph of function p of x, which is a multivariate function. So in this case, if the graph of d phi is also Lagrangian, simply means that they coincide whenever it is the function is locally defined. So it means that phi of x is an integral to the primitive of the form PDQ. So, and this is good away from the turning points. It's when this variety ramifies. So let me call this variety lambda, where lambda ramifies. And again, from the deformation quantization point of view, like looking earlier, so we can say that the works of Maslov and Leray, they extend, so they construct an explicit module over this ring, so explicit construction. Of a W module. And strictly speaking, we need to twist it with a half form, so associated to any smooth Lagrangian. So including the turning points. So, and this was also clarified by Nest and Siegel, which was the precursor of the work Boris was talking yesterday. So all the formulas of Maslov, they simply mean that we have an explicit mode. Complex? Oh yes, but up to this, so this was clarified by Nest and Siegel. Yeah. So if you look into formulas, so he says, okay, so here, so if it projects on this thing one-to-one, then we use this. Projects on this one-to-one, we use the Fourier transform in some formal way. Yes, yes, but it was all clarified by. Yes, yes, yes. One has to be. Yes, yes. So it means that there is the ring is defined without the model being defined. So anyway, so this is the formal structure, which is not difficult to understand. It's completely clear from the deformation quantization point of view. But it's interesting to look at explicit examples of such one-parameter families. And so it's easy to construct them in one dimension. We basically take one differential equation depending on the parameter, whichever way we want. So it's many for x equals 1, and rather few for dimension of x greater than 1. So the most naive way would be to write a pencil of flat connections. So a single differential equation. We can write it in a matrix form as a flat connection, but then, so it's very restrictive. So if you want to write pencil so then, what do we write? We write a differential equation of the form some chosen connection plus tau a. D tau, so should be flat for every tau. So it means that this is flat, first of all, and then we expand and we say that d0 of a is 0, and we say that a wedge a is 0 in omega 2 tensor and e. So and this gives a so-called spectral cover. Let's again call ch tau inside t star x. But it's not easy to construct forms satisfying those two properties. So and one example which is sort of explicit is the so-called Knizhnik-Zamolodchikov equations. We say x equals Cn minus diagonal. So the vector bundle is trivial with the tensor product of several representations of a group, reductively a group G. So the first connection is D, and A is some omega ij to logarithm xi minus xj. So those are the Casimir operations. So that's one of the few cases when we can simply write this equation and say, okay, we have an actual pencil. And this has been studied from WKB point of view by Reshetikhin. So, in fact, more or less, all explicit examples are connected in one way or another with group actions, with some kind of representation theory framework. So we are looking for families of D models. Which we can write down. So basically, somehow the real sorts of example, we would consider representation theory of a group G when weights go to infinity. Now, for example, we can see for SL2, we can look at asymptotics of 6J symbols. So this is one classical context for SL2. But let me consider like two rather simple examples, which we can write down and sort of understand what's going on. It is, again, very elementary. The first example would be the Harish-Chandra system for characters. First. This would lead to terminating WKB. So basically, it's a system of equations on a function, u, on the semi-simple Lie algebra G, which somehow what equation would be satisfied by a character of infinitesimal character of an irreducible representation. So there are two sets of equations. The first equation is the invariance under conjugation. And second, it should be the eigenfunction, should be the eigenfunctions of Laplace operators. So the Laplace operators correspond, they lie in center of the universal enveloping algebra and correspond to invariant polynomials that might like this symmetric algebra of the Cartan subalgebra. So then we fix the common eigenvalue. So we fix mu and H star. This would correspond to characters of representation with highest weight mu. And we simply say that delta P of u equals value of P on mu times u. So the simplest example would be the group SL2. Say G equals SL2. Simply a three-dimensional space. So in the real form would be SU2, R3. So the conjugacy invariant means that this function only depends on the radius, and the Laplace operator is the usual Laplace operator. Look at radial eigenfunctions. Delta U, so with a U of R. Delta U equals, in this case, would be mu squared times U. And I recall that in terms of R, it would look like this. It would be U, second derivative of R plus 2 over R, first derivative of R equals mu squared times U of R. Now, in this case, everything can be understood directly, and so the characteristic variety. So what we do, we now take, so since there is a free parameter, we take mu equals tau times some nu. And tau, since tau goes to infinity. So we can apply WKB. So we can say what is the characteristic variety. So it will live in G cross G star. It is the cotangent bundle, which we can identify by Killing form. Is G cross G. So the first system invariance would give us commuting variety C inside xy such that xy is 0. And the second would be would give us g times the orbit corresponding to nu. So in the intersection, so the intersection would cover g in a finite way. So C intersected g times O nu covers g in this way generically. And this, of course, this is the rank of the Harish-Chandra system in the first place. But WKB, if you write it down, it terminates after, gives exact solution. For instance, for SL2, we get a radial function. We get something that is u of r would be e to the plus minus tau times r times 1 over r. It's exact. It's the so-called Yukawa potential. And this is an exact solution. So this is the first WKB term R0 and R1 as. And this has an explanation because the system can be obtained as the push forward of a rank 1 system from a cover which is generically finite to 1. So the reason it terminates, so because the system equals R by star of a one-dimensional system from the projection is generically double to 1. And this was explained in the paper of Hotta Kashiwara. I think only the first one. So just this type of behavior. Yes, well, it has. You see, it's singular at 0. Yeah. So basically, as I said, so most of higher dimensional examples are direct images of something one-dimensional from auxiliary spaces, and this sort of can explain the behavior. So now let me consider another example, which is slightly more involved, or maybe even less involved, depending on the point of view. It is the hypergeometric system of A. So here there was terminating WKB, and here it will be reduced to stationary phase. So instead of the semi-simple group, we start with a torus. Again, it sort of goes under the rubric of systems corresponding to group actions. We have torus of rank n+1. So with coordinates, say, x0, xn, we take a representation of this torus, direct sum over some characters, n, z to the n+1, of one-dimensional characters. So a representation. We assume it has simple spectrum, which means that each c chi comes no more than once. So then we have the infinitesimal generators, xi z over dxi, infinitesimal generators. So it acts on V and V star. So in this case, we have one more assumption. We assume so the chi lies in an affine hyperplane. So typically, we can just simplifying say that each chi has the form that the first coordinate is equal to 1. So and those omega now lies in subset A inside z to the n. So what we have, so let me make some picture here. We have this affine, this hyperplane with first coordinate 1. We have the origin. So we have this set A, and we have here the polytope. We have the Newton polytope Q, which is the convex hull of this set A. And because this line is an affine plane, we can take the cone over this. And call this cone K. It's the cone. Then we can identify the dual space with the space of polynomials. So in the individual basis vectors of this space V correspond to monomials, and the linear combination of monomials is a polynomial. So we can say that the dual space V star will be identified with C to the A, which is the set of polynomials f of x equals sum omega and A omega x to the omega. So it's a function in n variables, C star to the n to C space. So we ignore the first coordinate. So in this situation, we have inside V, we have the toric variety Y, which is spectrum C of Z to the n plus 1 intersect with K. Is affine, homogeneous because of this condition, conic toric variety. So we can make somehow picture like this. Let's just something like this. So and then we choose an infinitesimal character. So beta, which is beta 0, beta n, is a character from the infinitesimal Lie group of our torus. See? Yeah. So into this we associate a system of equations, or the same as a D module. So system and D module called H sub beta. So system would be on a function phi on the space of V star. So this is the hypergeometric. So A hypergeometric. It was introduced by Gelfand, Graeff, and Zelevinsky. And similar to the Harish-Chandra system, it consists of two conditions. First is the quasi-homogeneity. Which means that when we apply infinitesimal generators, equals beta I times phi for all I. And second, that for every polynomial E on V annihilating annihilating the variety y, or any equation of y, we have the corresponding differential operator with constant coefficients, which informally means that the Fourier transform of the function phi lies on that variety. So this is an explicit example of a holonomic system. It's one of the few examples we can simply write down. So it is known. This is holonomic. And generic rank of this holonomic system. Generic rank equals the volume in the appropriate units of the polytope. And in particular, the Gauss hypergeometric function f(1), they correspond to the case n equal 2, and the set corresponding to the 4 points in the circle. So in this number, the degree is the degree of this hypersurface y. So what happens if we write the characteristic variety or characteristic cycle, we intersect this with the highest symbols of those things. So and then we get a multiplicity here. Multiplicity will be equal to the volume of Q. So now again, since we have more than one parameter, we can simply let the parameters go to infinity. So now fix alpha in Cn plus 1 and put beta equals tau alpha and let tau go to infinity. So this is a classical setting in theory of hypergeometric functions. It's going back to Watson, 1924, F21. We can understand what the characteristic variety will be. So this deformed characteristic variety, we call it lambda. So again, it will lie inside V star cross V. So where did I make this equation? So this is independent on tau. So condition number 2 will simply give me V star times y. But condition number 1, instead of cutting like this, it will be cutting in a variable point here. So I'm the one intersection with high multiplicity will be replaced by several intersections with multiplicity 1. It would be variable, now affine section. Affine section. So we'll get something non-homogeneous, and it is not hard to see what we get. Formulate a simple proposition. So assume alpha is generic enough. So alpha lies in this in the complexification of this space. So it's a point somewhere here. I assume alpha does not lie in a complex linear envelope of any face of K. Then lambda is we can say what is the generating function of lambda. Of differential of a function which associates something to a polynomial will be f. So let me write it down and then explain where it comes from. We can write simply called the critical, it would be a multivalued function. I could say the critical value of the following thing. It looks like some kind of Legendre transform. Alpha 0 log f plus some alpha I log xi. So it has many critical points and many critical values, but this is the graph of the multi-valued function. So it's some kind of the explanation of this is that it can be sort of seen from, it's more elementary than this, but it can be seen from, let's say, it matches the integral representation. Of solutions. Which of the following functions. Phi of f, if I write integral over some cycle in the torus, and here I write f to the alpha 0, product xi to the alpha I dx. So for a fixed equation would be beta I, and I will like beta I equals tau alpha I. So then it's simply the stationary phase for this. So this is. So it's almost the same as the context, which so it's a partial particular case of the context which Jan was talking about, except here take logarithm, which is a minor modification. Let's look at a particular case. So what would be the simplest example? Well, if we take alpha to be 1, 0, 0, so then the condition means that we want to drop all the alphas. The condition means that the origin, so if 0 doesn't lie in affine, complex affine envelope of any phase of the Newton polytope, then lambda equals the graph of d log of critical value of or d of critical value of log f. So in particular, under this assumption, the number of critical points equals the volume of the polytope. So one can see, if you think of a polynomial in one variable, starting from degree 0 and going to degree n, that the number of critical points is less by 1 than the degree. But that's eliminated by this condition that it's not, 0 doesn't lie on the boundary of the polytope. So this is a variety which we can sort of understand. It ramifies. So let me imagine something like this. All right, so lambda. So in particular, it has the ramification points or simple turning points. So this is similar to what Jan was talking about. It's the situation when two critical points collide in the simplest way. So it's so when two critical points collide and form an A3 singularity. So f equals 0. Sorry, it has an A2 singularity. Would be something like x1 cubed plus some xi squared. So what will happen, say, in one dimension is for this point, we'll have a curve like this. For this and for a point nearby, we have a deformation like this. With two critical points sort of disappearing. So in this way, we get on one hand an explicit holonomic system, and on the other hand, since we can take A as big as we want, we have a good approximation for the space of all functions, so to say. So for A large enough, C to the A approximates space of all functions. And we can see the phenomenon that we should generically appear in the space of all functions. So now let me discuss my next point, which will be what if we try to look at the analogs of Stokes curves in this situation. Let me call this part Stokes geometry. And syzygies among elementary matrices. Among elementary matrices. So I recall the classical definition of the Stokes curves. So classical. Dim x equals 1 case. So x is a curve. The variety lambda is also a curve. Another curve. So we can write as a graph y equals p. We can write y equals p of x. And we look at a simple turning point. Let's call it point z0. So z0. Turning point. It means if it's a simple ramification, means there are two branches here come together. And if we sort of move a little, we can denote them by separate letters, like two branches. Merge. So then in this case, the Stokes curves emanating from this point are Stokes curve. I give all the condition that we can say that imaginary part from the integral to x of the difference of two branches, p1 of q minus p2 of q, from z0 to x equals 0. So in this, known to separate the asymptotic solution. So it would go like this. Three branches will come, and they separate asymptotics. Separate WKB asymptotic solutions. So we can call this curve, if it was P1 equal P2, then we call the whole thing C12. So all three of them can be called C12. So and then when the equation is of the second order, then that's all that happens. But for higher, we locally think that there are two branches. Yes, like plus square root minus square root for two variables. For a cubic polynomial, so we have this function and this function. Look at the difference. But now it was sort of slowly coming to the surface, and was the paper of Berg, Nevins, Robbins, 1992, and then Aoki, Kawai, Takei, and then more recently by Gayota, Moore, and Nitsky. Then when degree, so this is, suppose this degree is n to 1. So we have a sort of ordinary differential equation of order n. The so-called new or virtual turning points. So what can happen that there may be several points, like sort of more than one different curves come from different branches. So that what can happen, naively, that would be a part of Stokes curve C12 coming from merging branch 1 and branch 2. And this is a part of a Stokes curve C23 coming from branch 2 and branch 3. And in this area, so here, so asymptotic, not fixed. Because two things, we don't know which is bigger. Asymptotics, not determined. So, and what happens in this case that there is another new curve, so new Stokes curve, C13 coming from here, separating the regions. So in this, we keep doing this for a higher order equation. They sort of keep branching like this, and they form a network. That's what they call a spectral network. Or sometimes this may be not needed. Sometimes the intersection is only apparent, and there is no interaction. And that basically happens when they correspond to two pairs of branches which don't know anything about each other. Or it may not be needed. And then the picture would be something like this. Would be curve C12, and this would say curve C34. There is no interaction. Let's try to see what happens somehow. What should be the analog of this for the hypergeometric system? So in principle, somehow this approach can be, this can be defined for any ramification even in higher dimension as well. So it will be some kind of wall coming out of the ramification locus. So let me say that. Harmonic demonics. It would be interesting to understand. But at least let's look for the hypergeometric system. So again, in this simplest case, where we have just one coefficient, let's call it h, right, tau 0, 0. So then a turning point z0 will correspond to a polynomial f0 with A2 singularity. So in generic deformation, it will be a Morse function. So generic f near f0 is Morse. So and this A2 singularity gives me two Morse critical points. Now, the condition of the imaginary part of the integral simply means the condition on imaginary part of the integral P1 minus P2 dq means that a real, so suppose we have two Morse critical points, let's call them x0 and x1 and x2. That real log f of x1, which is logarithm of absolute value of f of x1, equals real log f x2, which is logarithm absolute value of x2. Should probably say, I should probably should have taken the imaginary part here, actually. Yes. I should probably take the imaginary part. It just doesn't really matter. It will be easier to write. So it will be argument of x1 is argument x2. So then the wall, what really happens is that generically, real part of the so for f Morse, so the logarithm of absolute value of f, which is a real part, logarithm of f, is again a real Morse function with all critical points of the same index. But existence of a gradient trajectory between two critical points of the same index is a codimension 1 event. So exists. So for this we introduce, choose a constant, a Keller metric on C star to n. So then we have a gradient flow. This is a gradient trajectory from x1 to x2. So basically, we can say that the Stokes wall corresponds to such ways of unfolding this point. There is a gradient trajectory of the logarithm of absolute value of f. So basically, picture would be something like this in one complex variable. There's one critical point, and there's another critical point here. So normally it goes like this, but sometimes it goes like this. It would be exactly 1 for in general. So the walls, at least near the turning points, they correspond to existence of such trajectories. So crossing a wall corresponds to an elementary transformation. Crossing wall. So elementary transformation, say, of thimbles. If it would be T1 would go to T1, and T2 would go to T1 plus T2. So it would correspond to an elementary matrix E12, which is 1, 1, 0, 1. Now, in general, since such transformations are in more complicated cases will be still of this nature, we can look at the group SL and Z. So, and it has elementary matrices, let's call them EIJ. It's a matrix which has one and just one more unit at position IJ, and zeros everywhere. So, and they know they satisfy the classical relations. They satisfy. First, there will be condition that if I do EIJ and commute with EJK, I get EIK. If IJK distinct. Or if they don't know anything about each other, then they simply commute EIJ, AKL equals 0 if J not equal to K, I not equal to L. So, and this can be written geometrically. This commutativity of two elements is written as a square. like this, say Eij, EKL, EKL, Eij. And this I can write as a pentagon. So it's even better using this relation, it's even better to write like this. Eij, EKL equals EKL. Yeah. No. So far I'm writing for a group. Oh, I'm sorry. Oh, yes, sorry. One, of course. Yeah, of course, it's one. One, of course. Yes, a group. Yeah. So I can write it like this: EKL, EI. Sorry, EIJ, EJK equals, sorry, EJK, EIK, EIJ. In view of the second one. So we will have such commutator. With the EIJ, EJK, EIJK, EIK, EIJ. Now this matches those two behaviors. So this is the pentagon and this is the square. And sort of the reason why this thing is needed here is because one can say that we can understand this simply by looking at behavior of such elementary matrices. Now it is a classical fact that, maybe I'll keep this. That those relations, they almost determine the group of integer matrices. It's written in books on algebraic K-theory, and I think this particular class fact is due to Magnus. At first, for n greater or equal to 3, these generators and relations. That means we forget about matrices and just say, let's look at the group with these generators and these relations and nothing else. So define a double cover. So we have SL2Z double cover, central extension. So SL and Z, yes, SL and Z, 1. Here we have plus minus 1. But this cover has a topological nature. It's from universal cover of SL and R. And second is that if we consider only triangular matrices of this nature for the generators, Eij, 1 less or equal to I less than J less than N, and the relevant relations, well defined precisely, now without any cover, the group of upper triangular matrices with units on diagonal. So one can say that that is the matrix algebra which tells us how such Stokes curves they should branch. Yes. I'm telling that like the simplest instance. Yes. And so from this point of view of gradient trajectory is the case when we have just one trajectory, or it's a sort of case of two trajectories. Let me get to this in a moment. How much time I have? Oh, okay. Now, in general, so let's try to understand a little more. So again, some general remarks about presentations of groups by generators and relations. So in general, a group, a presentation of a group by some generators. Let me call them EI and relations. Let me call them RJ. Is topologically, it's simply a two-dimensional CW complex, because every relation we can always visualize as a polygon. So it's the same. This is a two-dimensional CW complex. That's called B2, because it's two-dimensional, with one vertex. And fundamental group equals G. Now I want to refer to my rather old paper with Masahiko Saito. So it's not a Saito, not Kyoji Saito, not other Saitos people know. It's a Japanese-American mathematician from University of Florida. Paper called Hidden Stash of Polytopes. So we can extend this point of view, and by saying that, like for usual modules in the commutative case, we have generators, relations, and then syzygies, which are relations among relations, and so on. So here we can also say something that we can call a syzygy among the Rj. So it would be an element of the second homotopy group of this complex. It would be a polyhedral sphere which is glued out of whose boundary is composed out of such polygons. Is a polyhedral sphere in B2. And a complete system of syzygies, like a resolution, would be an explicit, not two-dimensional complex, but full cell complex, who is a classifying space of the group. So full chain of syzygies in a CW model of BG, whose skeleton is this two-dimensional thing. So and now, since crossing like such a wall corresponds to elementary transformations, so this is a general phenomenon about Morse functions on a manifold, a real Morse functions on a manifold, not necessarily on a complex manifold. But since if we take the set A large enough, then we can model any generic behavior. So let me just say that if M is a C-infinity manifold, say Riemannian manifold, then we can first have a space of Morse functions. But not every Morse function gives a cell complex, because we need a condition known as the Smale condition, basically saying that such things, such catastrophes, don't happen. They're called Smale functions. For which the dimension of the set of gradient trajectories between critical points x and y is equal to the differences of indices minus the index of y minus 1. So in particular, for a real part of a holomorphic function, this will be 0 always. Generically, there should be no trajectories. So in the complement is the so-called Smale discriminant. So it's an object of codimension 1. It's a certain system of walls. And it is known how it intersects in itself in codimension 2. And that's precisely this type of behavior. So it's probably even before work Berg-Nevrons and Robbins. So in codimension 2, sigma ramifies or self-intersects. Yes, yes. As either like this or like this. So in particular, so again, it's easy to see in 2 dimensions. So in case of real dimension of m equals 2, and say index being 1. So this would correspond to we have 3 critical points. So suppose you go like this. So and this sort of comes point xi, or say xi, and here we go into the critical point xj. And here we end up. So normally we go either this way or this way, but in codimension 2 it can happen that it can go this way to the xk. So and we can break down this in 2 ways, and we can break down this in 2 ways. But one of those 2 ways, there will still be an additional ambiguity. And therefore, there will be 5, not 4 ways to break this down. Yes. Maybe they will be different, but at least this thing, possibly, but somehow topologically, so there is 5 ways to break it down, and in general, so those ways somehow are. So if you have more than 3 points, so then let me just take a little more about this. Yes. Yeah, yes, no, I'm not saying that all of them sort of will be exactly the same, but we can see like certain next level. We should be able to see certain next level ramification patterns. So what I want to say that if X is an algebraic curve, then doing this, as you say, for real part, we see only those, but we don't see higher self-intersection patterns. So for X, see a curve, so generically, no other intersection patterns I see. So, but if what I say, if M, now if we relate to this case, M is C star to the N, then we can consider, instead of this diagram, we can consider sort of approximate diagram where we can approximate, or we can try to approximate by the corresponding set of logarithm of absolute values of functions from CA, for which are Morse. So in particular, logarithm of absolute value of f is Morse. And inside, we can say that f, of which logarithm of absolute value of f is small. So and then would be the complement of sigma A. Again, will be some union of walls, and gives a model for Stokes walls. So it means that higher codimension, so in general, higher codimension strata. So why did I start talking about this? So higher codimension strata of sigma and of sigma A will give higher syzygies among elementary matrices. So a stratum would give us a pattern of trajectories. So stratum is a pattern of trajectories. So in particular, we have, let's look at codimension 3 strata. So a set of strata in the sigma, they would correspond, so this corresponds to the pattern where we have 3 critical points. So now I'm going to coordinate a strata in sigma. Oh, yeah, real. Oh, yeah, real, yeah. So they would correspond to patterns. The simplest pattern would be like this. I, J, K, L. So the codimension is the number of those coincidences. Or there will be a pattern like this. The number of errors. I, J, K, L. And products. And also some products when two things don't interact. So and this will be visible in families where more than 2, with 3 real parameters or 2 complex parameters will be visible in families. So they would correspond to polyhedral syzygies. So as I said, a polyhedral sphere whose boundaries are built out of those things among this relation and this relation. So, and in particular, if I call just right this A and this B, the stratum corresponding to the A is the Stashov polytope. It would be, this is the situation when it's sometimes good to have a computer like this. This would be a polytope with 6 pentagons and 3 squares. So what I mean that it would be dual diagram to intersection of walls, like if you take a transversal slice, then in 3-dimensional space there will be walls with this many chambers, and each edge correspond to the actual wall, it would be combining together like this. And in the case B, so in the case B, we have this and this commute, and each of those pairs, they form a pentagon. So it would be something like this. We start with IJ, E, IK, would be E, JK, would be E, IK, EJK, and then on each of them, we go upwards, we write EKL, so it will terminate in pentagons. So, and then there will be one more thing here, will be something like a pencil. And so it would be another type of intersection with walls. So my conclusion is that these pictures and more complicated ones would generically appear because if we have in the Euclidean space, we have this intersection, and we automatically have some sort of polyhedral syzygy. So my conclusion, that these and more complicated and more higher dimensional syzygies patterns will appear for Stokes walls of holonomic denominators. And of course, this will be very interesting to study this. Okay, thank you so much.